the next thing I want to do is I want to talk about when I would recommend that you think about column partitions. And the way that I want to do this is I want to say, let B, the vector B, and perhaps we're going to call B an element of Rm. So B an element of Rm. Be a linear combination. What does it mean to be a linear combination? A set of scalar vector multiplications and vector-vector additions. The output of a linear combination, a single linear combination, is always a vector. So in order to define a linear combination, what do I need to have? What do I make linear combinations out of? A set of vectors, right? So it'd be a linear combination of vectors AK, where k runs from 1 to n, which immediately implies what? B is equal to what? x1, a1 plus a2 plus, yeah, why don't we just do one more for the sake of it? And then we go all the way down to what? xn, an. Now what? Let's go ahead and write this out. And let's think about this as the first column vector that we're working with. And this is the second column vector we're working with. And let's go ahead and label it as such. So what would this be? 1, 1. What's the next one? 2, 1. And then we go all the way down to m1, because those were all m by 1s. I didn't explicitly write that. How would you have known that I meant those to be m by 1s? Say pattern recognition, Anderson. Yeah, okay, what's the next one? 1, 2, because it's the first entry in the first row, always has row index 1. It's the second column, so the column index would be 2. What's the next one there? 2, 2, all the way down to m2. And that's going to be an m by 1. Let's do the third one. So this is x3. What does this look like? A1, 3, A2, 3, all the way down to m3. And that, of course, is an m by 1. And we go on and on and on until 1n, 2n, mn. And that vector is now an m by 1. Could you rewrite this? Is there a way that you could imagine how to define a matrix out of those? What would this be in a matrix? Yeah, this would be x1 times the first column. And then this would be x2 times the second column. And then this would be x3 times the third column. And I would keep going until I got to xn times the nth column. Let's go ahead and write that, grouping these together. So what does it look like if I were to now group these in terms of a column partition? So this would be A1. What's the next one? A2. Maybe I'll skip the third one for now. And I go all the way to the end until I get to an. And this matrix now is an m by n. What's the vector that I'm multiplying by? x1, x2, all the way down to x what? Yeah, why was it xn? Because how many columns did I have? Yeah, I needed an entry of x for each individual column, right? Why did I need an entry in x for each individual column from the standpoint of a linear combination? Okay, the inner dimensions must agree is actually a realization. Yes, you're right on. That's beautiful work. I didn't see your flag, though, so I'm a little bit disappointed, right? I had a student once in one quarter that actually made a flag. She came to class with it. It was like a paper flag, right? She didn't embroider it, which I was a little disappointed. But yeah, what does it mean to take a linear combination? I need a scalar for every vector. Well, how many vectors did I start with? N of them. So how many scalars do I need? n of them, and that's the statement of the inner dimensions must agree. The statement is, if I create a linear combination out of n vectors, every vector should have its own scalar. The inner dimensions must agree. Now we have A times x. So this is what I would call an m by n. This is what I would call an n by 1. Here's a question that I have for you. Where is the matrix? Is the matrix on the left or is the matrix on the right? On the left. Here, remember that when we're thinking about this function, the matrix vector multiplication function, the first question that I would ask you is, can you tell me how to solve the matrix vector multiplication problem? How do I solve that problem? And please use this terminology right here. The solution to a matrix vector multiplication problem is what? It's a vector. It is a linear combinations of the columns of the matrix,
and the scalars of
where the kth column is scaled by the kth constant in my vector. Say that again. What is the solution to a matrix vector multiplication problem?
It is a linear combination
of the
columns of the matrix scaled by the kth column scaled by the kth constant.
Yeah, or I scale the first column by the first entry of x. I scale the second column of A by the second entry of x. And I keep going until I get to the nth column, which I scale by the nth entry. In this particular function, what is given, what is hit? What's the input? What am I changing in this function? Am I changing A or am I changing x? X. So where is x? Is it on the right or is it on the left? Yep. I'm going to say this right now, and we'll come back to this over and over and over again in this lesson, the next lesson, the one after that, and then beyond, beyond, beyond. When I'm doing a matrix vector multiplication problem, or when I'm doing a matrix multiplication problem, and the thing that I'm trying to change is on the vector that I'm working with is on the right, and the matrix that I'm working with on the left, I'm going to cut my matrix into what? Columns. And then I'm going to take linear combination of the columns using individual scalars from the vector.